Good morning, students. Today we are going to discuss UV visible spectroscopy. In that, different kinds of spectroscopies will be used for the determination of the component, different types of component. Uh, what is spectroscopy? Spectroscopy is the branch of science dealing with the study of interaction of electromagnetic radiation with matter. It is further defined as it is a measurement of electromagnetic radiations, EMR, measurements of electromagnetic radiations absorbed or emitted when molecules or ions or atoms of samples moves from one energy state to the another energy states. If atoms in ground state, it absorbs some kind of energy in form, it will go to the ground state to higher energy states. Then it will emit some radiations, which is electromagnetic radiations, or absorb electromagnetic radiations, which is followed on samples absorbed by atoms. Spectroscopy is the most powerful tools available for the study of atomic and molecular structures. It is used in the analysis of wide range of samples. Now, what is the principle of spectroscopy? The basic principle of spectroscopic techniques is based on measurements of spectrum of samples containing atom or molecules. Spectrum is a graph of intensity of absorbed or emitted radiations, both types. It will be absorbed of radiations or it will emit the radiation, which is graphically prepared by sample versus frequency or wavelength. Spectrometers is an instrument which is designed to measure the spectrum of compounds. So basically, two types of spectroscopic techniques. First one is absorption spectroscopy. Second one is emission spectroscopy. In absorption spectroscopy, sample or component absorb radiations which is generated from source. Absorption spectroscopy is the analytical techniques which concern with the measurements of absorptions of electromagnetic radiations. Here is the examples of absorption spectroscopy is ultraviolet spectroscopy, visible spectroscopy, infrared spectroscopy, and ranges of electromagnetic radiations. In UV visible spectroscopy are 200 nanometer to 800 nanometers. In these, UV range is 185 to 400 nanometers and visible ranges from 400 to 800 nanometers. In IR spectroscopy, 0.76 micrometer to 50 micrometer. It is diagnostic results for the analysis of compounds. In emission spectroscopy, the analytical techniques in which the emission of particles or radiations which is dispersed according to the some property of emission and the amount of dispersion is measured. It means molecule absorb some radiations which is go from ground state to higher energy states. Then after it will emit the radiations then emitted radiation will be measured. For example, mass spectroscopy. Now, what is electromagnetic radiations? Electromagnetic radiation consists of discrete packets of energy which called as photons. And photon consists of an oscillating electric field and oscillating magnetic field, which are perpendicular to each other. Here is the diagrammatically presents. Electromagnetic radiation go from this way, that is magnetic field, and some radiation go from this way in red circles, that is electric field. Both fields are generated and these radiation go to the perpendicular plane to the proportion of light. Now, what is wavelength? Some terminologies which is held for the determination or analysis of compounds. Wavelength. What is wavelength? It is distance between two successive maxima or two successive minima of an electromagnetic waves. That is called as wavelength. The units are meter, centimeter, millimeters, nanometer, and micrometers. Or sometimes it will be defined as it is the distance between two discrete or creased or two troughs of electromagnetic waves. Okay. Frequency. What is frequency? Frequency is the number of wavelength unit passed through the given point in unit time is called as frequency. It is denoted by nu, and units are cycle per second or hertz. Now next terminology is wave number. Wave number is, it is defined as the number of waves per centimeter in vacuum. Is reciprocal of wavelength and denoted by nu bar. Nu bar is equal to 1 divided by wavelength. What is velocity? Next, it is the product of wavelength and frequency, and it is equal to the velocity of wave number in medium. So V is equal to n into lambda. The relationship between the wavelength and frequency can be written as C equal to nu lambda. Okay. A photon is subjected to the energy. So capital E is the energy, is equal to h nu is equal to h c by lambda. What is c by lambda? C by lambda is the first relationship between the wavelength and frequency. Put the values in nu. Okay. So it is converted into hc by lambda. Next one is energy levels. Three types of energy levels in UV spectroscopy: electronic energy levels, vibrational energy levels, and rotational energy levels. First one, electronic energy levels. At room temperature, the molecules are in lowest energy levels, E0. When the molecules absorb some kind of energy, electromagnetic radiations, which is UV visible lights, ranges from 200 to 400 nanometers. One of the outermost bond or lone pair of electron is promoted to the higher energy state, such as E1, E2, and so on. It's called as electronic transition levels. The difference is as delta E is equal to HV is equal to En minus E0. And energy is 35 to 71 kilocalorie per mole. Vibrational energy levels, these are the less energy level than electronic energy levels. कंपैरेटिवली अगर आप इसको देखेंगे तो इलेक्ट्रॉनिक एनर्जी लेवल के कंपैरिजन में वाइब्रेशनल एनर्जी का लेवल कम होता है, लो एनर्जी के साथ में ट्रेवल करता है. molecules. The spacing between energy levels are relatively small, that is 0.01 to 10 kilocalorie per mole. For example, when IR radiation is absorbed, the molecules are excited from the vibrational levels to another, or it vibrates with higher amplitudes. Rotational energy levels. These energy levels are quantized and discrete. The spacing between the energy levels are even smaller than the vibrational energy. The order of these three energy levels are delta E rotationals is less than delta E vibrationals is less than energy as compared to delta E electronics. It means the higher energy required in delta E electronics. The electronic transitions. Now, transition between the molecules. The different types of electronic levels are possible. First one is that sigma antibonding transitions and sigma antibonding transitions. Basically, four types of transitions. First one is sigma antibonding and sigma antibonding, pi antibonding, and pi antibonding transitions. Now, first one sigma antibonding transitions. And electron in bonding s orbitals is excited to the corresponding antibonding orbitals and observed with saturated compounds. These type of transitions possible in saturated compounds. The energy required is large. For example, methane, which has CH bond, and in that case CH is a covalent bond and can only undergo sigma antibonding transition. So an absorbance maxima at 125 nm. Absorption maxima due to sigma antibonding transitions are not seen in typical UV visible spectra 200 to 700 nanometers, but in UV region 125 to 135 nanometers. And sigma antibonding transition, the saturated compounds containing atoms with lone pairs, unbonding electrons like oxygen, nitrogen, sulfurs, and halogens are capable of and sigma antibonding. These types of transition usually need less energy than and sigma antibonding transition. They can be initiated by the light wavelength is in the range from 150 to 250 nanometer. The number of organic functional groups with and sigma antibonding peaks in UV regions is small. Now next one, pi antibonding transitions. Pi electrons in bonding orbitals is excited to corresponding antibonding orbitals, pi antibonding, and observed in conjugated compounds. Conjugated compound means C double bond C, single bond C, double bond C, like that. Compounds containing multiple bonds like alkenes, alkynes, carbonyl and nitrile groups, aromatic compounds, etc. undergo the pi antibonding transition. And for example, alkenes generally absorb the region in between 172 to 205 nanometer. And pi antibonding transitions. Next one, an electron from the non-bonding orbitals is promoted to antibonding pi orbitals and require lower energy. Comparatively, it is less as compared to sigma antibonding, and pi antibonding transition requires minimum energy and so absorption at longer wavelength around 300 nm. Is diagrammatically presentations, sigma bonding and sigma antibonding. It means जो यहाँ पर सिग्मा डाउन में है वो उतना ही ऊपर जाता है. अगर सेकेंड नंबर पे पाई है, पाई उसके बीच में रहेगा, पाई एंटीबॉन्डिंग. तो इस बेसिस पे आप एनर्जी लेवल देख सकते हैं कि सिग्मा और सिग्मा एंटीबॉन्डिंग का एनर्जी सबसे ज्यादा होगा और वेवलेंथ रेंज कम होगा. ठीक है. नाउ नेक्स्ट वन, chromophore. Some terms will be used in UV spectroscopy. Chromophores, the part of molecule responsible for imparting colors, are called as chromophores. Or further type, it is defined as functional group containing multiple bonds capable of absorbing the radiation above 200 nanometer due to the transition of the pi antibonding and pi antibonding transition. For example, nitro groups, ठीक है, NO2 N डबल बॉन्ड O ग्रुप्स, कार्बोनाइल ग्रुप्स, साइनाइड्स, ठीक है, आइसोसाइनाइड्स, अल्कीन्स एंड थायल ग्रुप्स. Oxochromes, the functional group attached to a chromophore which modify the ability of chromophore to absorb light, altering the wavelength and or intensity of absorptions. Further, it is defined as the functional groups with non-bonding electron that does not absorb radiation in near UV region, but when attached to a chromophore alter the wavelength and intensity of absorptions. If we have to determine the cutoff value for the methanol, and these values are 205 nanometer. This solvents is used for the determination of paracetamol and paracetamol containing hydroxyl group, which alter the values of solvents. So it is oxochromic groups. In case of benzene, phenols, anilines, that is the examples. Absorption and intensity shifts in UV spectroscopy. Now ग्राफ, यहाँ पर एक ग्राफ बना हुआ है, तो इसमें आपको एक y एक्सिस पे एब्जॉर्बेंस शो हो रहा है और x एक्सिस पे वेवलेंथ है. तो जैसे आपका पर्टिकुलर कंपोनेंट होते हैं उसके अकॉर्डिंग ये शिफ्ट इंटेंसिटी शिफ्ट होता है. तो पैथोक्रोमिक शिफ्ट, व्हाट इज पैथोक्रोमिक शिफ्ट? व्हेन द एब्जॉर्प्शन मैक्सिमा ऑफ अ कंपाउंड शिफ्ट टू अ लॉन्गर वेवलेंथ, इट इज नोन एज पैथोक्रोमिक शिफ्ट. And hypsochromic shift, when absorption maxima of a compound shift to a shorter wavelength, it is known as hypochromic shift. Hyperchromic and hypochromic effect. Hyperchromic means when the absorption intensity epsilon of a compound is increased. If the hyperchromic shift, absorption of the intensity is increases, intensity increase, that is hyperchromic. And intensity, absorption intensity is decreases, ये absorbance है, और absorbance के रिस्पेक्ट में अगर देखें तो absorption intensity उसका डिक्रीज हो रहा है. So it is called as hypochromic effect or hypochromic shift. Okay, now okay, is it clear?